So we'll continue with the 13th lecture of characterization technique, and as promised, I'm not going to talk about more about SEM today, but something which is even more fundamental, which basically called the electron matter interaction. So whenever we have the electrons incident on your sample, be it a biological sample, be it a nanomaterial, be it a bulk sample, some kind of interaction happens, because of which we have got different kinds of signals which are coming out of the sample, and these signals are trapped in and fed into a detector to study the property of the material. So these signals that are coming, their intensity, their energy, okay, and the type of signal that is getting generated all defines the property of the material that you are studying. So this is the reason that electron matter interaction becomes a very important part of the study. So as we go with the future classes where we study the transmission electron microscope, this is going to be helpful, and as a result I feel that this is very important to learn at this point. So when we have the primary incident electron onto your sample, okay, we are not defining the sample as of right now. We are considering all the possible kinds of signal that can be generated. Please remember, it's not mandatory that a sample will generate enough amount of any of these signals to actually give you a result. Okay, it can generate only one kind of signal, okay, or it can generate some kind of signal, and might be there are very less secondary electrons, so you cannot study the secondary electron much, or for example less characteristics and so on. So it's like a possibility or a combination of all the possible signals that can be generated. So when a primary electron is incident on a sample, you can have a backscattered electron, we have studied about this. We can have secondary electrons, we can have characteristic X-rays, we can have something which is called cathode luminescence. I think you all know because of luminescence, something to deal with light and photons. If you are not clear, you can refer to my previous lecture. And of course Auger electron, but these are not this is not exhaustive. There are other phenomena that also happen, because in transmission electron microscope we read the other kind of electron which is actually transmitting through the sample. Okay, so basically what happens is, if we consider something as scattering, so what happens is that the electron is incident on the sample and then there is scattering. Now this scattering might be elastic or inelastic, okay, and based on this we have got the signals which are getting generated. So we are going to see those kind of elastic and inelastic scattering. So as I said, when the electron beam hits the sample, it will interact with the atom in that particular sample, and definitely the outcome will be the electrons. For example, some electrons will bounce back out of the sample, these are called backscattered electron. Others actually knocks into the atom and displace the electron, which in turn come out of the sample, these are called secondary electrons. So we have a primary source, and basically it's knocking out an electron which was present inside the sample, inside the atom. Those electrons coming out are called the secondary electrons. Alternatively, we have got X-rays. Okay, so X-rays are also definitely there. These are the characteristics X-rays. So if you want to know what kind of material it has, if you are having a compound, and if you want to know the component of the material, you can definitely use this X-ray for EDAC study. So we basically have light or heat in the sample. Okay, so we have got light and heat in the sample. So this is actually the maximum amount of energy which is used from the external source. So these are coming out in the form of heat or light, okay, or basically a dispersion. So then we can say that most of the energy that is there, as I said, is dispersed as heat. So these electrons are collected. Okay, so it collects the electron coming out of the material in order to produce the traditional SEM images called micrograph. Who collects it? Basically a detector. So you basically have a combination like scintillator detector, you've got catalytic detector, you've got the EDAX setup, and scintillation detector, you're again connecting it to a photomultiplier tube, and then it is getting multiplied, the signal and all. Okay, and then finally you are going to get the SEM image. So we know about SEM images, how they are formed and all, because we have learned exhaustively for this. So basically what happens is, when we talk about SEM, the volume involved in the production of we are considering a particular volume, okay, and this volume is called the interaction volume. So this interaction volume actually has secondary electron, backscattered electron and X-rays in case of SEM, okay, and it will basically form into a shape. It will form a shape. This is called the interaction volume, which might be in the form of a teardrop or in the form of a semicircle within the specimen. So it will be I'm not that good at drawing, as you all know. It will be something like this, okay, like a teardrop, okay, or a semicircle within the specimen. We are going to see it in the next slide. And the diameter will depend on kilovolt. That means how much energy the incoming electrons actually have, okay, and of course the density of the specimen. So if the incident electron beam is able to penetrate, definitely the diameter will be more, and it can only penetrate if there are less number of atoms. But if it's got a packed system, we have got more and more atoms, the density is definitely high, hence the electrons actually cannot penetrate deep into the system, okay. So that means the diameter will depend on the density of the specimen. So it's approximately the top 15 nanometer of the volume comprises the zone from which the secondary electron can be collected. So if you want to collect the secondary electron, basically this gives a surface morphology. This is actually collected from the top 15 nanometer of your sample. So if you have got some samples, okay, and you are putting it onto the instrument, the top 15 nanometer will actually comprise of only the secondary electrons and also some backscattered electron. But the backscattered electron will also come from deeper within. So the top 40% of the region, which will actually give you the backscattered electron, and then X-ray is something which can be collected from the entire region. So if you consider the entire region, we can actually collect the X-ray from there. So if you just look into this particular animation, you can go to this side to look into this animation, but I think this slide is enough to understand this. So you see that the electron beam actually is incident. Then we have got the auger electron, the secondary electron, the characteristics X-ray, cathodoluminescence, secondary fluorescence, and of course heat, okay. So what happens is the secondary electron is only from this much region, the backscattered electron is from this much region, and the X-ray is basically coming out from the entire region, okay. The entire region actually is going to give you out the X-ray, but most of the electron beam's energy is also lost in the form of heat, okay, in the form of heat. So we can see this, okay, and then we have also got something which is called the secondary fluorescence, and then this secondary fluorescence you can actually relate it with the cathodoluminescence. So you put your detectors at different positions to detect these signals and analyze the samples. So this is a very important image, and if you can see there, we basically have a diameter and so on. So when we look into the electron matter interaction, it can be either elastic or inelastic in nature. And I don't think I need to explain this much. In elastic scattering, as you all know, the kinetic energy and momentum is conserved, and if momentum is conserved, that means we are talking more or less as the velocity is conserved or constant, remains constant, right. So basically what happens is the electron trajectory within the specimen may definitely change, okay, but in elastic scattering, theoretically the kinetic energy and the velocity remains essentially constant. So if there is slight variation, we usually consider that to be almost elastic in nature for all experimental studies. That doesn't differ much with the main result, okay. So the result will be basically nothing but the generation of backscattered electron. So if you think about an objective question, backscattered electron is a result of elastic scattering or inelastic scattering. So it will be elastic scattering. Now most of the times the incident electron trajectory is only slightly perturbed, but definitely the energy is lost through the transfer of energy to the specimen. So there will be some kind of change, and if even if there is some change, it's not too much, okay, but then there is some energy, okay, which is lost. So this actually results, or these inelastic scattering usually results in a number of phenomena. The first is the phonon excitation, which is nothing but heating, okay. I don't get confused between photons and phonons, okay. So phonon is the lattice vibration because of which you are getting generation of heat, and photon is the particles, okay, the particles. So you have to basically consider these differences. So don't write down photon in place of phonon whenever you are writing down any kind of answer related to this. Next we have got the cathodoluminescence, basically the visible light fluorescence, And then we have got the continuum radiation, bremsstrahlung. We have all studied about these things. Just to remind, bremsstrahlung, we have the electrons okay, coming out from the electron beam, which is coming out and basically incident on the atom. The atom basically has got a nucleus which is positively charged and the electron is negatively charged. So it basically gets slowed down, because of which there is something which we call as the deceleration, which is nothing but the bremsstrahlung, because of which some radiation is given out in the form of X-rays. Next, we definitely have the characteristics X-rays, okay, the K alpha and the K beta lines, if you remember. And then we have got the plasmon production. So plasmon production refers to nothing but the secondary electrons, and definitely the electron Auger electrons. So there is something which is called the Auger effect. You can refer to, you can just Google it, okay. But in general, we can say that this is nothing but the ejection of outer shell electrons. So if the outer shell electrons are basically ejected, these are called nothing but the Auger electrons. Because when we say have the inner shell electrons getting ejected, the outer shell electron comes and fills those spaces, releasing characteristic X-ray. So there is a difference between characteristic X-ray radiation, because which happens because of the inner shell electron displacement, and Auger electron, which happens because of the outer shell electron displacement. So we have to just remember the differences here. So then we need to have a specific system or a specific procedure to prepare the sample in case of SEM characterization, and this is where we actually say what we do is coat the sample. So if you are doing any kind of SEM characteristics characterization in your project, or when you do your PhD work, you will be asked whether your sample is conducting or non-conducting, because in order to get a signal we should have maximum number of secondary electrons coming out of the sample, okay. So if you consider something like heavy metal like gold or platinum, they are basically used to coat the samples. So you basically have an extremely thin layer of these gold or platinum which is being applied, okay. So please remember, this is nothing to do with matter interaction, okay, but indirectly in a way we want to generate more and more secondary electrons. So that's why I'm just discussing this, how to prepare SEM, okay. So basically this is nothing but SEM sample preparations, okay. So we have just doing a part of this, okay. Because we have studied the interaction and we see that number of signals come out, but in order to study SEM we need to have secondary electrons, but we don't have that much signal of secondary electrons. So can we do SEM? The answer is yes, we can do it, but we need to have a coating, okay. So this coating is basically applied because of two main reasons. No, it's a non-conductive specimen basically are often coated to reduce surface charging. So basically what happens if it is a non-conductive sample and electrons are basically coming in, there is something which is called the surface charging. If there is surface charging, the secondary electrons are screened, okay, or blocked, and it doesn't reach the detector. So I don't want to do that. So what I do is I basically coat it, and this will actually free the path of the secondary electron, and we can get a good image. On the other hand, if you get something which is having a low atomic number specimen, for example the biological sample most of the times has got a low atomic number, we will be getting a very less number of secondary electrons. We need to get more and more secondary electrons, and that is also a reason we basically coat the surface layer, and this will actually yield higher number of secondary electrons from the specimen material, okay. So that's there. And so if you just look into this table for sample preparation, it's basically a very big table, okay. You can again go to this MyScope website. In fact, if you are doing SEM, you can take a printout of this and put it in front, okay. So if you basically consider a sample, it can be wet or it can be dry. Now if it is dry, most of our problems is solved, but in general if it is wet, we mostly don't do a normal SEM analysis. We can actually try to dry it. So it's if it's not a biological sample, it's a normal sample which has absorbed some moisture from the air or during sample preparation, we can definitely dry it and go for the conventional SEM. But on the other hand, if we don't want to dry it and we want to actually do the studies, and let's say it's a biological sample, we can actually do something which we call as the environmental scanning electron microscope and so on. So you can look into this part here. But on the other hand, if it is dry, we can actually do both the topographical and the compositional study. For compositional study we can use attacks and all, and for topographical study we can use the secondary electron and the backscattered electron detectors, and then we can have the sample in the form of bulk, okay, mostly not nano samples, and then we can have it in the form of powder, okay. So then if we have a compositional sample, we basically have a smooth surface. Okay, so if it is yes and it is conductive, we can actually go for polishing. If it is no, we can directly go for the studies. Okay, so we can basically do the studies here. If it is conducting, and then we can actually go for the studies. If it is not conducting, we can go for polishing, or we can go for coating, as I told you in the last slide. Okay, or we can actually also do a carbon evaporating coating for some specific sample, and then go for the SEM studies. Okay, and after the SEM studies, we can also do the EDS study to do the compositional analysis. So if you look into this chart, okay, you can understand it. Okay, and this is basically a flow chart as such. Don't worry, I am not going to ask you in this in exam. This is only for your knowledge purpose. If you are interested, you can definitely look into it from a closer perspective. Okay, but please don't ignore the basic things. Okay, so if I ask you that if I have a sample and if it is wet, what should I do, then definitely you should say that the first stage is to dry it if it is not a biological sample, or a sample which will always remain wet even if it is dried. Okay, so these kind of questions definitely might be there. So you have to study the flowchart. I'm not going to ask you to draw the flowchart, of course, but there can be some certain objective questions from the flowchart. So please don't ignore it. You have to definitely study it in a better way. So finally, if as I said, if we have got a material with a higher atomic number, this diameter is definitely affected. If we have it with a lower atomic number, the incident electron or the electron beam can penetrate deeper, and we can actually have a larger diameter. Okay, so we basically have a low voltage and a high voltage region, and from this we basically get all the signals that are possible. Okay. So that's all for today. See you in the next class.